Apologies for the less funny title. So what I'm going to start with is running real malware. But first, where did I come from? So I've been playing with JS for quite a while already, and I joined MetaMask a while ago. I know barely anything about crypto. I don't own any crypto. I just work on securing JavaScript in which MetaMask, the wallet, is written. And this is an interesting case because if a package in our dependencies gets in and manages to run its malicious code in the wallet already, there's no longer any point saving or mitigating anything. It's already too late. So we need to stop it, assuming it already got in. So everything I work on is with the assumption that all the earlier defenses failed, or that all the scanning of the packages, the whole CVE system already failed us, and we're already running in production, whatever you think in production means, but we're already running in production with malicious code inside of our code base built into one bundle for the front end, or running in the CI, or running in the backend process of Node.js, and so on. So that's where I'm coming from. And you can go to my website and look at stuff there. So this is going to be a little bit like, if you know the first threat responder ever, Clifford Stahl, who's a great guy. He had a TED Talk. It was beautifully chaotic. I'm hoping to achieve something like that. Okay, and I always start with this question. So would you accept a string of text from me, and without reading it, put into your JavaScript code base and ship it to production? Raise your hand if you would. No? No one? Why? Okay. Would it help if I put it in a tar.gz file? Anyone? If I compress it into a tar.gz file? No? Why? That's what NPM packages are. Code from other people you don't know that they put in a tar.gz file. And these are no different than user input from the internet. And you're putting them in your application and running them as code all the time. And we're doing it all the time. We're consuming NPM packages. I've been doing that for many, many years, and it was great. Speaking of many years, I've been interested in supply chain security for a while. So I first started looking into vulnerable dependencies. So before NPM Audit existed, there was Node Security Project. Node Security Project had a tool that was a command line tool, kind of similar to NPM Audit. I played around with that. At the time of the first publish of NPM Audit, I put it in CI as one of the steps. And my team hated me for it because we had our CI monitoring red almost every day because of it. So I had to go and invent a thing that would let us selectively ignore things without compromising our security posture. That's NPM Audit Resolver from many years ago. I don't even remember now. Then I turned my attention to malicious post-install scripts, which is also fun. It's great fun. And there's Lava-Mode allow scripts, spoiler alert, and a small tool that I built to help you figure out which can be ignored safely. And that's also a story available, recorded on my website. And then I went and learned about hardened JavaScript, and this is what we're going to talk about today. Previous editions of this are also on the website, but today there's something fresh, so stay up for it. And then this is the workshop from yesterday. It's been happening already a few times, and I'm going to do it on CEFCON. If you missed it yesterday, you can go to CEFCON and attend that workshop. All of that available at my website. Okay, now watch me run actual malware. Okay, so where do you get malware? If malware ends up on NPM, it's quite often that before you get to download it, it's already blocked because someone spotted it, right? And you get a page that says, oh, this was malware. Okay, so if it's not there, you can use socketdev Well, you can use socketdev for things for which socketdev exists. I recommend it. But you can also use it for taking a malicious package, that's already known malicious package, and then going to socket and exploring its files and downloading some and running them. That's fun. Okay, so yeah, we're gonna run a malicious package that I found, and it's gonna be obfuscated. Okay? So is that a problem? Well, we can use the obfuscation, but the specific one I stumbled upon was obfuscated 4 times, and I manually went and deobfuscated it 4 times, and the last time I deobfuscated it and run it, it went into an infinite loop because it could detect that it's been deobfuscated. And I didn't find the infinite loop. So yeah. But then I thought, I'm working on tools that protect software from malicious packages at runtime. So I control what they're doing at runtime. So maybe instead of disallowing things, I'm going to use that to just see what's going on. And this is, warning, this is a toy project, okay? This is not an actual malware analysis lab. So this is what, sorry for your eyes, this is what the code looks like. And this is a terminal. So I've already spun up the lab. I'm not going to go into details of how it's made, but it's very simple, an idea that just runs it without network access, just in case. And I have a bit over 100 of lines of JavaScript for this command. And I have a malware called LoffyGang in here. It's from a few years back. Okay, it's checking if we're actually offline. Okay, and obviously if it's a live demo, I have to be cheating. So I have a pre-recorded session of this, and I can, instead of remembering what to choose on each step, I get help. But, so what's happening here? At the top, you see an empty object, and that object is going to grow with notes of what this software was trying to reference from the global scope. And then it's going to ask me if I want to run certain things or not. So I've been deobfuscating it manually, so I know that eval is used for deobfuscation steps. So I'm going to allow it. And then regular expressions are also used for deobfuscating. And there's, as I said, 4 layers of obfuscation in there. So we passed through that. And some parse ints. OK. And now we're starting the actual program. Again, I didn't have to deobfuscate it with any software because the code has to deobfuscate itself so that the JavaScript that's obfuscated can be interpreted, compiled, and run. What's the first step? They want file system. Should I give them file system? Nope. Should I give them HTTPS? No. Should I give them glob? No. Should I give them child process? No. Okay, now they want to run exec from child process. Okay, so I have this chain of things that it was trying to access. What am I going to give them? I'm going to give them a fake function. Okay, require an HTTP client, as if you didn't already get one. Do we want to give them access to process? Nope. Okay, so what's process going to be? It's going to be a proxy. All right, what's process.env? Also a proxy. Now they're reading local app data from process.env. Now we know it's a Windows malware, so I didn't need any isolation for this. Okay, but still, let's go. Now they want to list a folder. So what I did here is I returned a recognizable string as local app data so that when it pops up somewhere else, I can know that it's the same string. Okay, so reading a directory, fake function. Okay, and now they want to read this directory. So we now know that this malware is reading local app data to see what's there. Why? Well, they're iterating through the folders in there. And with this iteration, They're calling stuff and checking if it includes something. And the includes function gets this string as input. So now we know this is malware written by teenagers who want to steal Discord server credentials from other teenagers. Okay, and then they're executing task list for whatever reason. I'm not really sure. Someone knows? Maybe it's just for funds. Okay, what's next? Now they're taking Axios, which is an HTTP client, because the HTTPS module from Node was too difficult to use. And they're using it to post a request to Discord webhooks. So why set up your entire infrastructure for data exfiltration if you can just use a dummy email to set up a Discord server and use webhooks to post to it? You're already a teenager experienced in reading the most obfuscated stuff on Discord, right? Okay, and that's it. Runtime ends. Ta-da! Okay, that's what the malware is doing. And I didn't go through any deobfuscation here. It deobfuscates itself so that it can work at runtime. Well, isn't that fun? This tool isn't fully secure because it doesn't support ESM modules, so import-export, because I don't have enough time in my life for this. But why stop at obfuscation? So I gave this talk before, just without a few sections here. And someone asked me, hey, what if the malware is not delivered as obfuscated JavaScript, but as JavaScript bytecode that was previously compiled? And I said, what? Yeah, that's possible. So if you have an Electron app or a Node.js app, you have access to a module called VM, which can take code as a string and compile it to bytecode for you and run it in some context. But it can give you the cached compiled bytecode, and if that bytecode is then compatible with the next process you want to run it in, it's going to run. It's going to take it from cache instead of compiling the same source again. So it's just a mechanism for caching things if you want to read some code and you don't know if you end up reading the same code twice. But this tool checks if the cached data matches the sources that you're trying to compile. And what's the check? Well, it would be kind of wasteful to keep all the sources along with the bytecode for just checking the cache. So the cache key is, as you can see here in the spoiler, length of the input. So all I need to do to run bytecode is to give input as code that's matching length for the original bytecode, the code that produced that bytecode, right? And that means I can compile to bytecode, save the length, and then only deliver the bytecode payload as my malware and run bytecode without ever revealing the source code. And deobfuscating JavaScript is a much more solved problem than decompiling JavaScript bytecode. So can we use the same tool for running bytecode? Kind of. Okay, simple example. This is just an example bit of code, and that code was compiled into bytecode. Do I want to click it? Yeah. So we have this file, and I can now do this. Okay. Oh, since we have panels, let's look at the code while I'm doing it. Okay, so I'm not running a.js. I'm now running c.jsc, which is, by the way, the result of compiling a.js in here. It's written here. we take a.js and writing it back to c.js after compilation. Okay, so let's quickly go through it. And this is bytecode that's running, and I plugged this bytecode runtime into the same tool. So we're getting, oops, wrong button. Okay, we're getting console, which is a global. We're getting URL, require fs, calling read file sync on the payload. We decide to return a string, and then that string is being passed to eval, and eval complains that string 0 is undefined because it actually ran. And that was compiled bytecode. Okay. That was fun. But where is it all coming from? So the way to do it is bits of code that I stole from a project I'm working on called LavaMoat. If you need a sticker looking like this, come get me. I have stickers. And LavaMoat is a tool for protecting JavaScript software at runtime, because we control, if you need more proof, I don't know what else should I show you, we control what's happening at runtime. Okay, let's back up a little. How do you deliver a supply chain attack? There's post-install scripts, which is a vast majority of everything that happens on NPM in terms of malware. So most people don't really want to write JavaScript. They prefer to write bash if they're attacking. And you can put bash in the post-install script. And it's easier. And you use typo squatting as one of the means of getting to the end user, the developer who installs something. And then your post-install script runs and can do absolutely anything as the current user, including the current user of the CI system where the build is running, which is getting increasingly fun. You can also use dependency confusion, which is an incredibly boring topic, and I'm very grateful to Liran Tal for exploring it all the way through so I don't have to. You can also do package takeover, and the famous package takeover of event stream is what inspired LavaMoat. So my friend who started working on LavaMoat from nothing woke up one day to news on a news portal that a well-known crypto wallet was attacked by its supply chain, and bad things happened. And he happened to be the founder of MetaMask, so he got a bit scared and worked on LavaMoat for the next 2 years. Okay, you can then use prototype poisoning, which if we end up having time, I might dive deeper into. Maybe. Oh, oops. But prototype poisoning in a JavaScript application is like lateral movement in the network. So you can go somewhere where you're not supposed to go with prototype poisoning. Yeah, and please don't publish malware to NPM for any reasons. Even for good reasons, it's not allowed. Even if you're doing security research, it's not allowed. People do it anyway, but yeah, don't. You're wasting good people's time when you're posting your malware that you want to use for penetration testing requested by a company into NPM. All right, so my hat is actually blue, right? Yeah, so let's talk about defenses. First, reactive defenses. So we have NPM audit. NPM audit is there, and I was trying to be polite with the text here, but NPM audit is there to tell you that, hello, you've been running this malicious package for 2 months now. Want to do something about it? Then you can use socket dev, which is much quicker, because in a few hours from publication, they already have results. These results are not coming from people researching the malware and doing a CVE process and getting results 2 months later. This is coming from heuristics, analysis, pattern matching, and even AI. Should have put it in the title. It would make getting into conferences much easier. So what socketdev does, it warns you that this package kind of looks malicious for these reasons in these files, or this package is doing these unusual things. Look at it. You have to have time to look at it, or you have to have people motivated to look at it. That's a totally different problem. And then there's seal security, which I recently added. These are some folks with a tiny startup just booting up, where they're backporting fixes to known vulnerabilities with fixes existing for latest version. But if you're stuck on an NPM package that's 5 years old and you cannot upgrade to the current major version for a security fix, they're backporting security fixes to old shitty versions, which is all too common for big companies to be stuck on. All right, but we want to be proactive, not reactive. So instead of reacting to someone or something finding and fixing a problem, or just finding a problem, we want to prevent problems from being possible. This is secure by design versus chasing after vulnerabilities and issues. So what do we want to do? Let's take a look at defending from packages. The whole thing that Lavamoat is built on top is called hardened JavaScript. Hardening should be a common term here. Not going to talk about it. Did you know JavaScript happens to be designed in a way that's good for security? I hear the laughter. I expected the laughter. So you know how JavaScript is being developed? There's ECMAScript, which is a standard, which is built in the ECMA consortium by TC39, which is a group that does these things. But that's just a language. So, you know, in Python, if you get Python, you have ways to make network connections built into the language. They're specified by the same people. They're available from the same sources. With JavaScript, you get just the language, and then there's W3C for the browsers and Node Core for Node.js, and then whoever at Dino coming up with ideas on how to expose powerful APIs to the language. Now apply Conway's law. Conway's law says an organization is going to reproduce its communication structure in the code. And this is what happened to JavaScript. There's very good isolation between the language itself and the APIs. So if we can control the scopes in the language, we can control what powers you have access to. The only way to reach anything powerful in JavaScript is to get a global or require/import something. And hardened JavaScript does exactly that. So hardened JavaScript is implemented as sesshim, which is an implementation. It's called a shim because if you want to demonstrate an approach that you want to put in a language, spoiler alert, you create a shim. So this is an implementation of hardened JavaScript with the intention to standardize it eventually. Compartment is for scope isolation. So you can create compartment, run code in that compartment, and it's within the same process. You don't get process isolation. You don't get thread isolation. It's code running with the same process with access to the same exact global references, but with enough isolation that we can decide which of those references are going to be available. And code from two different compartments can still call each other's function if they happen to be available by reference. And then there's also lockdown, which is a few thousand lines of code that makes the JavaScript environment safe from prototype pollution and all of the dangers with how the language was designed to be malleable. So it's using the malleability of the language to harden it. That's what lockdown's doing. Okay, so lockdown is, shortest version of lockdown you can use is object freeze on object prototype. No prototype pollution on object prototype is now possible. Imagine 5,000 more lines of this kind of thing, and we're there. Okay, so Lavamoat uses sesshim to protect the app code from malicious dependencies. We're taking compartments, putting each dependency in a separate compartment so we can control what powers they have available. How do you do that? You generate a policy. So you call auto policy on your code, on the entry to your application. A policy is generated. This is the only time at which we use any reading of the code and trying to extract things. So we generate a policy as best as possible. If we miss anything, it's not going to be available. If there's obfuscated code that's hard to figure out what it's reaching for, it's just not going to be available. And then you run Lavamode build.js instead of Node build.js, and it's using the policy. This is a tiny fragment of what the policy looks like. Once we generate it for ESLint plugin that depends on an evil package, you get information that it's reaching for request from HTTPS built-in, and that it's reaching for process.env from globals. If it's obfuscated, this is not going to be here, which makes it equivalent to this. You can also manually say that, no, this is too much. Least authority, okay? And we're running. So when you run your code with this policy, you get one of these errors, depending on which one's reached first. One is that evil package requested HTTPS, which was not available by the policy. The other option is you get cannot read env from undefined because, oops, process is undefined in Node.js. But don't worry, only for this package. Okay, what about browser apps? We have a Browserify plugin if anyone wants. But we also have a Webpack plugin in beta. Finally, took 4 attempts to make it happen. Yeah, so if we have time, I think we do, we can see it in action. Are you tired of looking at JavaScript already? Good answer, thank you. Okay, where did I put it? Okay, yeah, so we have an application here. Yeah, because I have some packages that should not exist on NPM, right? I have a package that I called Cookie Monster. And that package has a function called random quote, and when you call it, it gives you a random quote from Cookie Monster, okay? And there's also a legit dependency from NPM, one of the best ones. And then just to prove a point, there's some TypeScript involved so that I have something to build with this Webpack stuff. And then it's setting some cookies just to prove a point. And as you probably anticipate, Cookie Monster wants our cookies. And that's what's going to happen. So let me run a server here. All right, so I'm not going to run the build for the sake of time. I have pre-built folders where we can see what's going on. Okay. Yeah, let's open the network tab and refresh. Okay, okay. So what the app is doing is the app is getting a quote from Cookie Monster, getting a comment from the TypeScript code, and then printing out the stuff that it's set. And as you can see here, Cookie Monster is exfiltrating to example.com what our domain was and what cookies we had set. So let's look at the Cookie Monster for a second. Did I leave it here or did I forget? Oops, I forgot. Okay, so you're going to have to trust me that Cookie Monster is just using fetch to send it out. Or we can find it later in the DevTools. But if we go to a version that was built with Lavamode, and I can show you the policy, which should help. So this is the policy. The cookie monster was reaching for document cookie, fetch, and location host. But we override that policy to not allow anything. So if I run it in that version, we get errors. Fetch is not a function. So Cookie Monster failed to steal our cookies. I don't know about you, but that actually kind of makes me sad. Never mind. So I think we're very close to running out of time. So we're going to have to decide if we want to go into questions or if we want to talk about the lateral movement options for JavaScript, which is prototype poisoning. Raise your hand if you really need the questions time. Okay, so you can find me later, get stickers for that, and we're gonna delve into this thing. Okay, prototype poisoning. This is kind of a tiny fragment of the workshop last time. Do I still have 5 more minutes? Okay, so what's prototype poisoning? By the way, the difference between prototype poisoning and polyfills, which just introduce missing features to older browser, is the intention. The mechanism is exactly the same. So prototype poisoning is taking global prototypes and replacing some of the functionality on the global prototypes available in JavaScript itself. And now if you call toString on an object, even without realizing it, you're running someone else's code instead of what's part of the browser itself. And you get this, okay? So yes, this, JavaScript was designed in 10 days, famously. And what I find surprising in our industry is that the person designing it humbly assumed that it's not going to be perfect. That's unusual. So they left means to improve things. Yeah, I spoiled this one. So let's look at some attack examples from the workshop yesterday, if I dig them up in time. And I'm going to talk you through them just a tiny bit for our amusement. Is that supposed to be number 2? Yes. So this is the most typical prototype pollution attack. And this is an attack on the code that's in this file where we're setting secrets. So there's internals secrets, which is an array, and then we're putting secrets in there later, the actual secrets. And what's this doing is it's defining a new property on object prototype. So every object created anywhere is going to have a pre-existing property on the prototype called secrets. And that thing is not a variable pointer. It's a pair of getter and setter. So every time someone assigns to the field secret on any object that doesn't already have this field as its own property, the engine's going to climb up through the prototypes and call our setter with the value being assigned. And that's the most basic prototype pollution. Okay? Moving on, number 4, you can do the same with functions. So we can replace a function on array, and every time someone checks if something's in an array, you will get, well, we can ignore what they're checking, but you get the array. Same with any iteration, you can also do that. And if someone finds a way to prevent that from happening, you can also hook into calling functions if you want to, because calling functions in some cases is also a method on an object. Okay, that's fun. But the most fun is here. So this is the last example from the workshop. And what this is doing is, in the workshop, we improve the code until we reach a point where it's immune to prototype pollution. But then that code is calling fetch. And fetch in Node.js was introduced fairly recently by taking an NPM package that was implementing fetch and making it part of the core. So fetch in Node.js is written in JavaScript, and it uses the same globals. So if we hack into map, they're using map to arrange arrange headers, so we can grab authorization header from the entire process every time it's being set for fetch. And the only way to prevent that is to freeze the globals. But you can imagine how far you can pivot through an application by just being a package that provides no functionality but just happens to be imported somewhere. You can, through prototype pollution, pivot to absolutely anywhere in the application, no matter what scope and how tight the scope is for something else. So that's why we have lockdown. And I'm running out of battery, but I think I'm finished. Yeah, that's me. Thank you.
Thank you.